Welcome to science class. Today we are going to begin learning about natural resources and human impact. Everything we do requires the use of resources, whether it be food or livestock or mineral and metals or fossil fuels or even just water. We use these resources in countless ways. The way in which we have used them has also transformed greatly over time. Animals used to be our vehicles and our tractors, and our hands were our combines. The wind was our motor for navigating the globe, and running water was the generator that powered our factories. The ability to extract the unreal power locked inside the molecular structure of fossil fuels has given every man, woman, and child the potential power of thousands of his predecessors. The industrial and modern eras have really been the eras of productivity, for better and sometimes for worse. Let's get started. For today, we are going to focus solely on what energy is and the historical context of where we got our energy from. Energy is defined as the capacity to do work. In other words, energy is what makes things go or allows things to change. There's energy all around us, and it comes in pretty much two forms: kinetic and potential. Kinetic energy is the energy that a body possesses by virtue of being in motion. Isaac Newton's second law of motion states that force equals mass times acceleration. So a 1 kilogram object traveling at 10 meters per second has exactly twice the kinetic energy as another 1 kilogram object traveling at 5 meters per second. Examples of kinetic energy include the wind, flowing water, and the work that animals do. Potential energy is the energy possessed by a body by virtue of its position relative to other bodies, or stresses within itself, or electric charge, or other factors. The classic example is two rocks perched on two different ledges of different height. The rock that is higher up has more potential energy. It would produce a greater change if it impacted the ground. A spring or rubber band or bouncy ball has potential energy locked within itself. The atmosphere contains huge amounts of potential energy, which sometimes is manifested as a lightning bolt. Batteries have potential energy. They can make things go. Food is potential energy for both you and me and animals. Sunlight is also potential energy. And of course, the greatest source of potential energy are the hydrocarbon bonds of our fossil fuels. Well, greatest in terms of actual use. A 1 kilogram uranium rod has upwards of 1,000,000 times more energy stored within it than a kilogram of coal. We'll talk about that in another video. Historically, people used almost exclusively kinetic energy for the big stuff. Boats used the wind or flowing currents of water or human muscle. Planting and harvesting was done by hand and with animals. Travel was done on foot or by horse. Wars were fought with hand-swung weapons. And some cultures did find ways to manipulate water for manufacturing. Obviously, without food for nourishment, we couldn't have done anything. But we just didn't know how to find and extract large amounts of potential energy in any other ways. Wood was the only other potential energy resource. We would burn the wood to make charcoal, which we used to cook food and make stronger metal alloys for tools, but that's about it. We went about doing this for thousands of years. Now, people are smart enough that if you give them a couple thousand years to work on a problem, they'll figure out the absolute best way to solve that problem given what they have to work with. So, what were the results of thousands of years of harvesting the most readily available and ubiquitous energy all around us? Well, virtually everybody who wasn't nobility was a subsistence farmer. People regularly starved. It took 6 months to travel the Oregon Trail. It took Magellan 3 years to circumnavigate the Earth, and only 22 of the 270 crew members lived, Magellan not actually being one of them. And it took 80 camels or 30 horses to haul what a semi-truck can, and camels and horses only move 3 or 4 miles per hour. The amount of energy out there in nature truly is staggering. Between the wind and the running waters, and especially the sun, there's more measurable energy than we could ever consume, even with over 7.5 billion of us. The problem is that it's almost impossible to control these types of energy and make them do what you want them to do. So how do you calculate energy anyways? Well, we covered force equals mass times acceleration earlier, but that only applies to moving objects. How do you measure the heat output of something, or the ability of a system to generate electricity, or the potential energy of coal or a liter of gasoline? Turns out there are all kinds of ways to do this. The universal energy unit is called the joule. A joule is defined as the amount of energy required to push a 1 kilogram mass a distance of exactly 1 meter in exactly 1 second. This is also the definition of a watt, but watts are used to measure electric energy. See, you can convert any type of energy into another. The average fastball in Major League Baseball exerts 161 joules. You think of a Major League fastball, and that seems like it has a ton of kinetic energy. But guess what? A 60-watt light bulb produces the same energy in 2.7 seconds. Seem hard to believe? Here, watch this. This is an electric motor hooked up to a very low wattage light bulb. I have to exert a tremendous amount of work just to keep this terrible light bulb lit. When you turn on the lights, it feels like literally nothing has just happened, but the amount of power it takes to keep those bulbs lit all day is actually huge. A Tour de France biker will burn around 6,000 calories a day. If you hooked up one of those bikers to a stationary bike and configured it to capture and store electricity, those 6,000 calories would light a 60-watt bulb for less than 5 days. Some other units of energy include British thermal units, or BTUs. This is used with ovens and grills because it's defined as the amount of heat required to raise the temperature of a pound of water by 1 degree Fahrenheit, or 1,055 joules. Then there's the calorie. That's the amount of energy required to raise the temperature of a milliliter of water by 1 degree Celsius, or 4.2 joules. Now, when you read calories on food labels, that's actually given to you in kilocalories, which is usually labeled as just calories with a capital C. Since it's a kilocalorie, this is the amount of energy required to heat a liter of water by 1 degree Celsius. Horsepower is something we hear all the time, but nobody knows what it is. 1 horsepower is the work required to lift a 75 kilogram mass 1 meter in the air in exactly 1 second, or 735 joules. Torque is measured the same way, but with different units. If a car produces 400 pound-feet of torque, the pound-feet part is usually taken out, then that engine can lift a 400-pound mass 1 foot in the air in 1 second. For the rest of this unit, when we talk about energy, we will almost exclusively be talking about electricity, because civilization doesn't work without electricity. So we will use the kilowatt hour to put electricity consumption into perspective. A kilowatt is 1,000 watts, and a kilowatt hour is the amount of energy it takes to keep a 100-watt light bulb lit for 10 hours. 10 times 100 is 1,000, so there's our 1,000 watts. This equals 3.6 million joules. Before we wrap up, let's do some perspective taking. We already did this with the Tour de France example, but we're going to take that a little further. The average American burns around 2,000 calories in a day. That amount of energy would keep a 100-watt light bulb lit for 22 hours. So if you devoted all your effort in a single day to powering your own home, that's all you could accomplish. A 1 horsepower engine produces the same amount of energy in just 3 hours. If you take all of the appliances in your home and also factor in transportation and a few other things, the average American consumes around 186,000 what we call machine calories in a day. That's the work of 84 people doing nothing but eating and making electricity. The average household consumed around 900 kilowatts of electricity a month, which would be the work of 350 people. just for your electricity needs. A gallon of gasoline has the equivalent of 31,000 calories. That's what it takes to get a car to go 25 miles. When I said the industrial and modern ages are really the eras of productivity, now you see what I mean. The United States is the third most populous country on Earth, but that still only gives us 4.3% of the population. How much of the total share of global energy do you think the United States uses with a little more than 4% of the world's population? 30%, which is pretty incredible. The whole continent of Europe has over twice the population of the United States, but we still consume more energy than them. Our per capita consumption is the highest of any country in the world. To be clear, this doesn't mean that we are taking away energy from anybody. We just consume 30% of the electricity and energy that happens to be made. There's no limit to how much more energy could be produced. And indeed, as China and India become more industrialized, the share of energy we account for will go down as a percentage, but the total amount of energy we use will continue to rise. Next time, we are going to focus on fossil fuels and learn what they are, where they come from, and how they are used. Thanks for watching.